Hello, everyone. So before I start, just want to thank the organizers for inviting me to come today tell you about this topic, because I'm always happy to take any opportunity to talk about gravitational waves since, well, I'm quite biased, but I think this is one of the most exciting topics in physics today. And so the goal of this two-part lecture is for you to be able to see, to understand more or less what a gravitational wave is. So that's going to be the theory part. So what is this thing here? What are the expected sources of gravitational waves? So as you're going to see, there's going to be binary systems of black holes involved. And finally, we're going to talk about detectors, typically laser interferometer, kilometer scale laser interferometers, such as LIGO in the US and Virgo in Europe. And of course, the detections, because I'm sure all of you heard that last September, the 14th of September 2015, and the 25th of December last year, the LIGO interferometers, both of them, have seen gravitational wave signals for the first time 100 years after their existence was predicted by Einstein himself. So this was a huge event for physics, and I think it's worth going into some explaining here. So I'll assume that you don't know general relativity. I'll give you some sort of short qualitative introduction to the theory, because gravitational waves are a prediction from that theory. Okay? So the plan is going to be to first talk a little bit about general relativity, really in very simple terms. Then introduce the concept of gravitational wave. What is a gravitational wave? And in particular, I'll try to rely on a comparison with electromagnetic waves, because I'm sure that everybody is familiar with electromagnetic waves, and try to show you what are the similarities and the differences. Actually, there are many more differences than similarities. And today, the last topic we'll touch upon is the question of what are the expected sources of gravitational waves. Next week, we'll discuss the gravitational wave detectors, both existing ground-based detectors and plans for future detectors, in particular in space. And we'll finish with a discussion of the first gravitational wave observation that took place last fall. So most of what I'm going to talk about will be based on slides, but from time to time I'm going to go on the blackboard and sort of do some simple calculations and order of magnitude estimates. So that's how I want to do it, try to combine the two. And at any time, if what I'm saying is not clear, please stop me. I'm not going to rush into the material. I much prefer that I don't finish and don't say everything I wanted to say, but what I say is clear, rather than getting to the end and you have no idea what I was talking about. So please don't hesitate to stop me anytime. OK, so let's start with general relativity. So general relativity is a very old theory now. General relativity is a theory of space, time, and gravitation that was formulated by Einstein in 1915. And so far, it's still the best theory of gravity that we have. We've tested it for years, for decades, for a century now, and it has passed all of the tests with flying colors. It has predicted 3 outstanding new physical phenomena, namely the existence of black hole, the dynamical nature of the universe, and the existence of gravitational radiation. And we've now confirmed these 3 phenomena. We have no evidence that general relativity should be replaced by a deeper, better theory yet. We are, of course, searching, but it remains our best theory of gravity. So physically, it's very easy to explain, right? Newton told us that gravitation is a force between massive bodies, and Einstein told us that no, gravitation is not a force, it's actually just a manifestation of the curvature of space-time. Gravity has nothing to do with bodies, in a sense. It's a feature of the structure of space-time. And if the moon here is going around the Earth, it's not because the Earth exerts a gravitational force that accelerates the moon on its orbit. It's because the moon moves freely, doesn't feel any force, but in a space-time that is curved by the mass of the Earth. That's the basic physical idea. You have mass, it curves space-time, and then bodies move freely in that curved space-time. So since it's a question of space, time, and gravitation, we need to talk a little bit about space and time. And before 1905, we had pre-relativity physics, right? Galilean and Newtonian mechanics, and the way physics worked at the time, except for electromagnetism, was that we had basically physical phenomena in space, and we studied them a long time, right? There was a nice, clear split between three-dimensional space and time. We had this absolute Euclidean three-dimensional space and this absolute Newtonian time. We thought that everybody could agree on what time is. It's just one, and it's the same for everybody. And we study the motion of bodies, like these two particles, in space as a function of time. Time is just some sort of external parameter, okay? Well, in 1905, Einstein told us that this is not right. We had to combine, electromagnetism with Michelson-Morley experiment that told us that the speed of light is actually the same in all inertial frames, independently of the state of motion of the source. And so we had to replace this picture, and we now have a picture of space-time, four-dimensional space-time. Of course, here I'm removing one dimension of space, otherwise I can't show the picture. And this four-dimensional space-time is such that there's no absolute space, there's no absolute time, right? There's no notion of simultaneity anymore. But there is some absolute structure in that space-time, and that is the light cones, right, that I'm showing here. That's the path of light that is emitted here from a point, an event in space-time. And instead of bodies that move in space a long time, we now have world lines, right, for those particles. And geometrically, when we say that nothing can go faster than light, what that means is that the world line of a particle has to always be within the light cone at any point along the world line. Otherwise, it would mean that that particle here is going faster than light. So we've replaced this fixed stage of space and time by another fixed stage of space-time. And the next step occurred when Einstein went from this fixed space-time, Minkowski space-time of special relativity, to now a curved space-time. So we had to do that to introduce a relativistic theory of gravity. Now we had, electromagnetism that fit in the molds of special relativity, and also the other interactions. But gravity, we still had this non-relativistic theory, Newton's theory of gravity. So Einstein thought we need to have some relativistic framework for gravity. And the guiding principle to go from the left to the right was the so-called equivalence principle, which is based on the observation of the universality of free fall. Namely, all test bodies move along trajectories which are the same, universal trajectories, independently on their mass, and even more remarkably, independently on their composition. So this means that if bodies fall in the same way in some external gravitational field, somehow maybe gravitation is not a feature of the bodies, but a feature of space-time itself. And Einstein realized that he can explain this if space-time is actually curved. And so the mathematical framework is a so-called manifold, which needs not be r to the 4, and a space-time metric, G, which has some curvature associated to it, contrary to the flat metric of special relativity, the Minkowski metric. This metric can have some curvature. Space-time is curved, and in fact, it's curved by the mass and energy and momentum you have in space-time. So this is, okay, so this is another way to see it, the road to general relativity. Before relativity, we had three-dimensional Euclidean space that described a flat space, and we describe physics in that setup. If we now add time and we use the invariance of light speed, we go from pre-relativity physics to special relativity. The mathematical framework is Minkowskian geometry, a flat four-dimensional space-time. And if you now allow for curvature in your space-time, you get a curved space-time described by a Lorentzian geometry, in much the same way that you could add curvature to Euclidean space to get some Riemannian geometry describing curved spaces like the surface of a potato, for instance. And if you want to go from Riemannian geometry to a Lorentzian geometry, you add time in the picture, and your metric, instead of being a positive definite, actually has a signature with a minus sign, just like in special relativity. And so that's the setup for general relativity. So the core of the theory is just one equation, the Einstein equation, that relates part of the curvature of space-time. So you recognize here the metric, and these quantities here are so-called tensors that are related to the curvature of that metric, the curvature of space-time. And on the right-hand side, you have a description of the energy and momentum content in that space-time. Okay? If you add mass or energy, you're going to have a so-called stress energy tensor. And so when you have matter, it's going to curve space-time locally at every point in space-time through that equation, the Einstein equation. So in words, that means that matter tells space-time how to curve. And then you have the other side of the coin, which is that if you take the divergence of this equation, well, you have an identity on the left-hand side, which is that the divergence of this should vanish. This is the so-called Bianchi identity. And so that implies that the divergence of the stress energy tensor vanishes, which is nothing but a very elegant and compact way of saying that energy and momentum are conserved locally. And so that implies the equations of motion for matter. So the Einstein equation also tells you that space-time tells matter how to move. And then you can show that light, electromagnetic fields, move along null geodesics of that curved space-time geometry. And matter, with mass, like you and me, we move along so-called time-like world lines. And in particular, if we feel no force, like the moon moving around the Earth, then this will be a time-like geodesic. So a geodesic being the generalization for curved spaces and space-time of the ordinary straight line of Euclidean geometry. So that's all there is in general relativity. OK, so now you may say, this looks like a beautiful geometrical theory, but when do I actually need to use it, right? Maybe Newton's theory works great almost in every context. And so to answer that question, you need to consider a physical quantity that we call the compactness. So the compactness parameter is a dimensionless number that involves the gravitational constant and the speed of light, as well as the mass m of a typical physical system under consideration and the typical size r of that system. Okay? You take a physical system, roughly it has a size m, characteristic size r, and a mass m, and then you can compute that dimensionless number, the compacity. You can check very easily that it has no dimensions. And depending on whether this compactness parameter is very small compared to 1 or not, you will use a different theory of gravity. If the compactness is very small compared to 1, actually Newtonian gravitation will do the trick. But if the compactness of the physical system under consideration is of the order of 1, then Newtonian gravity is going to give you very poor predictions. And in fact, you need a relativistic theory of gravity to describe your system. You know, this is sort of like when you do hydrodynamics and you look at numbers like the Reynolds number because you want to figure out if you're gonna need to take into account viscosity, for instance, or not, right? You build a dimensionless number that tells you what is a sort of physical phenomenon that is important or not. So why is that so? Well, there are several ways to understand this. First, you can notice that this compacity is nothing but the ratio between the Newtonian gravitational potential of your physical system of mass m and the square of the speed of light. Well, I'm going to say roughly like. And if you remember the virial theorem, if your system is self-gravitating, then roughly as an order of magnitude, the gravitational potential should be of order the average velocity squared. And finally, if I consider some test body of mass little m here close to the surface of my body, then I can rewrite this as gmm over r divided by mc squared. And that is to say, this is the absolute value of the Newtonian gravitational potential energy divided by the rest mass energy. So clearly this is telling you that if the typical velocities are close to the speed of light, or the gravitational Newtonian potential close to c squared, or the gravitational potential energy close to the rest mass energy, then gravity and relativity are sort of competing on equal footing, and so you need a relativistic description of gravity. On the other hand, if your typical velocity is very small compared to the speed of light, if the Newtonian potential is weak field, or if the gravitational potential energy is small compared to the rest mass energy, then gravity is weak compared to relativity, and a non-relativistic description of gravity is good enough. You can use Newton's description of gravitation. So a proton, for instance, has a very small compacity. So you don't need to use general relativity to describe the physics of a proton. Similarly, for the Earth or the Sun, these are very small numbers, 10 to the minus 9 or 10 to the minus 6. So what this is telling you is that the general relativistic corrections to Newtonian gravity when you study the physics in the vicinity of the Sun are going to be roughly 1 part in a million. So if your experiment is not so accurate, Newtonian gravity is good enough. But if you make very precise observations in the solar system, for instance, of the motion of planets around the Sun, with an accuracy with 6 or more significant digits, then you will need to start taking into account relativistic corrections to Newtonian gravity. This is actually what is done at the Paris Observatory by people who compute ephemeride. I don't know how to say this in English. They predict the motion of planets around the Sun in the solar system, and they compare to the observational data. And in the analysis, they need to include so-called post-Newtonian corrections, the first corrections to Newtonian gravity, simply because our measurements are so accurate that you need to go beyond Newtonian gravity. So even for a system with a small compacity, you may actually need to take into account general relativity. But clearly, when you're looking at very compact objects like neutron stars or even black holes, then you would need too many sort of corrections, and so you really need to work with the full theory. You will need to use general relativity in particular to understand the physics of black holes. So we'll see that this notion of compacity is very important when we are studying sources of gravitational waves, because a good source of gravitational waves has to be compact. It has to be relativistic in the sense that the typical velocities are close to the speed of light, and also it has to be quite massive. Any questions so far? No? Okay. Yes?
Okay, no, just so there is no example in the universe with this number bigger than 1.
No, because
I guess because the universe
it's a very sort of order of magnitude number, right? Actually, in general relativity, the very notion of size is not so well defined. When gravity is weak, when space-time curvature is weak, you recover this picture with this absolute Euclidean space. And you know what you mean by the physical distance between two bodies. It's the usual Euclidean distance. But when you're in a very relativistic regime, when space-time is very curved, there's no well-defined notion of the size of a body. Qualitatively, there is, set up to a factor of 10. Okay? So when I put a number like, roughly 0.2 or so, just think like it's of order 1. But basically, I could define what I mean by characteristic size of a body such that I would get maybe 2. But what matters is that it's of order 1. Any other question? No? Okay. So let's now move on to gravitational waves. So as you would expect, in any relativistic theory, right, you're going to have waves. Like in Maxwell's theory of electromagnetism, you have this D'Alembertian operator, which tells you that there's going to be a finite speed of propagation of your waves. In Einstein general relativity, the Poisson equation, which involves this Laplace operator, which tells you that gravity propagates instantaneously, is going to be replaced also by a wave operator, because you're going to need to have the special relativistic structure that comes in. And that special relativistic structure with, these light cones and the fact that you can't go faster than light is going to impose some finite speed of propagation. So we expect to have gravitational waves in general relativity. And that's what comes out. So what is a gravitational wave? In simple words, it's just a tiny ripple in the curvature of space-time that propagates at the speed of light. So imagine that you have some background curvature. Say you have the, I don't know, some black hole somewhere, okay? It has some mass. It creates some space-time curvature, which I'm showing like in blue. It has some metric associated with it, that curved space-time metric. And now you imagine that you have some tiny ripples that propagate over that background curvature. I denote them as h. These are the gravitational wave, and you can show that they propagate at the speed of light. If you like equations better, it looks like this. If you take the Einstein equation and you linearize it around this background solution, you end up with a linear wave equation, okay, where this box operator here is not just a simple flat space-time box operator of Minkowski space-time, because this background curvature can have some curvature. So this is a bit more complicated, but it's still a box operator, like a D'Alembertian. And then you have a coupling between the background curvature of your space-time and the metric perturbation. The metric perturbation being the gravitational wave. And this can have a source, the stress energy matter that entered in the Einstein equation here, okay? So you basically linearize here this left-hand side around this background curvature space-time, and you get this equation. In the simplest case where the background is just Minkowski space-time, okay, so flat curvature, then there's no term like this because the Riemann curvature tensor vanishes, and you just have an ordinary wave equation for this h, little h, sourced by the stress energy of matter that can be in your space-time. So this is, as I said, a key prediction of Einstein's general theory of relativity, because in Newtonian gravity, you have no such wave, gravitational wave. Gravity does not, that propagates instantaneously. If I move the position of the sun, right away it's going to influence the gravitational field everywhere in the universe, okay? There's no finite speed of propagation of gravity in Newtonian gravity. In general relativity, there is. And so if the sun was to disappear right now, the Earth would keep going around for about 8 minutes for the time it takes for the gravitational wave to come inform us that there's no source of gravity anymore, okay? So geometrically, in a space-time diagram that looks like this, if you have space here and time here, you have the world lines of particles that are always at every point within the local light cone. And a gravitational wave can be seen as some sort of ondulation into that sheet of space-time. But what's important, it's not a wave that propagates in space-time. It is a part of space-time itself. It is a tiny ripple in the curvature of space-time itself, okay? So it's not separate from space-time. It's a part of space-time, this gravitational wave. And to better understand the similarities and differences, it's nice to try to explain how different they are from electromagnetic waves. So an electromagnetic wave is nothing but an oscillation in the electromagnetic field, okay? And it's sourced by the acceleration of a large number of small electric charges. While a gravitational wave, it's not a wave that propagates in space-time. It's actually a wave in the space-time curvature, and so it's part of the space-time. And the same way, if you accelerate an electric charge, you're going to produce an electromagnetic field. Well, when you're going to accelerate a mass, you're going to produce a gravitational wave. If I take an electron, okay, it has some electric field, and I accelerate it, there is a finite velocity of propagation of the information. The electric field is changing in time, and the magnetic field as well, and that information is going to propagate outwards. You're going to get electromagnetic waves. Exactly the same way, if I start with some mass, it has some static gravitational field, but now if I accelerate it, I'm going to locally change the space-time curvature, and that information is going to propagate upwards, and these are the gravitational waves. Another important difference has to do with the typical wavelength of gravitational waves, which are typically larger than the size of the source. What that means is that you're not going to be able to image your source with gravitational waves, contrary to electromagnetic waves, where typically the wavelength is much smaller than the size of the source, which allows you to do images. The structure of the electromagnetic field in the wave zone is predominantly dipolar, okay? And the coherence of the wave is fairly low. For gravitational waves, it's different. This bulk motion of large distribution of mass that are accelerated creates waves with a quadrupolar structure in the wave zone and with a very high coherence. So that's another important difference. Maybe the most important difference is the interaction with matter. You know that when some source of electromagnetic waves out there produces the waves, before they reach you, they're going to interact a lot with the matter in the interstellar or intergalactic medium, right? They're going to be absorbed, scattered, and so on. And so you may lose some of the information that you had originally when the waves were produced. It's very different with gravitational waves because they interact extremely weakly with matter. They virtually propagate undisturbed between the source and the detector. So the good thing is, if you manage to see them, they're going to give you great information about the source because they have not been polluted by everything that was in between. On the other side of the coin, if they don't interact with matter, they don't interact with the matter of your detector either, or very weakly, and that means it's going to be very hard to actually see them. Okay? This is why it's a huge challenge to detect gravitational waves. And finally, I'd like to mention that electromagnetic waves, we are rarely able to actually track the evolution of the wave itself. It's usually too high a frequency for the electronics to follow. So what we see is the average power in the field that decays like 1/r squared. So that decays fast. But as I said, it interacts a lot, so still you can see electromagnetic waves from very far away. For gravitational waves, it's different. When you hear people say the gravitational wave decays as 1/r, it's true. It's not the power. It's the field itself. It decays like 1/r. And because the typical wavelengths are not too small, the frequencies are not too large, we can actually track the change in time of the wave itself. And so even though the amplitude of the wave is small, since it decays like 1/r, we can still reach further out. If you want some analogy, one may say that so far astronomers have been looking at the universe, right, with light, but also with other electromagnetic waves, X-rays, gamma rays, X-rays, and so on. And with gravitational waves, it's very different. It's more like if you were starting to actually have a new sense, like audition, and you're sort of listening to the universe. Well, I'm not saying a gravitational wave is a sound wave, right? It's not a sound wave, but somehow, as an analogy, that's the way to think about it. These are really complementary sources of information about the universe. And that's why it's so exciting that we are starting to see or to listen to gravitational waves. It's because they are emitted by sources that don't emit, for instance, binary black holes, that do not emit electromagnetic waves. They are emitted in a regime where gravity is strong. Basically, we're going to be able to see physical phenomena that we couldn't see otherwise. And ideally, if you can complement the two, you probably can learn much more about the universe. Okay, this is my theory slide for those of you who like theoretical physics. There's another nice, neat little analogy you can make between electromagnetism on one hand and linearized gravitation on the other hand. So here I'm going to say that my gravitational wave is just a small perturbation of the flat Minkowski background of special relativity, right? Imagine that this background is completely flat. The radius of curvature is infinite. So there's no curvature, so there's no term here. So I just have a flat box operator acting on the metric perturbation, the gravitational wave, sourced by the stress energy tensor. So you know that in electromagnetism there is this gauge transformations you can do, right? You have a vector potential and you can shift it by the gradient of a generator of a gauge transformation. But interestingly, there are some things which are physical in the sense that they are gauge invariant, such as the Faraday tensor, which includes electric and magnetic fields that are invariant under such gauge transformations. While similarly, you can imagine that the gravitational wave, the metric perturbation, can be shifted under a gauge transformation which now involves some vector generator. And there is also a gauge invariant quantity associated with it, a physical quantity, and that's the curvature associated with the gravitational wave, the Riemann curvature tensor, which looks like that. So that's a neat analogy. Basically, you just add one index everywhere. And just like you can impose a Lorentz gauge condition in electromagnetism to get a nice wave equation for the vector potential sourced by the for current, you can impose a Lorentz gauge condition on h, or more precisely the so-called trace reversed h, and get the wave equation I mentioned before. So linearized gravity can also be formulated as a gauge theory, yes?
How do you understand from these equations that the size of the wave is bigger than the size of the source?
The size of the wave is bigger than the size of the source. So for most sources of gravitational wave, indeed, the gravitational wavelength is going to be much larger than the size of the source. This will be especially so for so-called post-Newtonian sources, where the typical internal velocity is fairly small compared to the speed of light. But I don't think you can see that from just that slide. Other questions? Nope. OK, end of the theory parenthesis. So what can we do with gravitational waves? Well, we're going to be able to do a lot of science. If you're interested in fundamental physics, for instance, you're going to be able to test general relativity, our best description of gravity, in the so-called strong field nonlinear dynamical regime. That is to say, when the predictions of GR are as far as you can imagine from those of Newtonian gravity. In the solar system, the compactness is not very large, right? 10 to the minus 6 at the surface of the sun. So deviations from Newtonian gravity are small. That's why we talk about post-Newtonian corrections to Newtonian gravity. So you can't test in the solar system gravity in its wildest dynamical regime. But when you have two black holes that orbit each other and collide, this is a regime where the compactness is large, where the gravitational field evolves very quickly, when you have waves emission. And so if you get those waves, you're going to get information about the state of space-time when it's very disturbed, when those two black holes orbit around each other. And that's going to provide you with new fundamental tests of gravity in that regime that has never been explored so far. People have just started doing this last fall with the first two detections of gravitational waves from the merger of binary black hole systems. Another thing you can do is test something called the black hole no-hair theorem, which I'll tell you a bit more about in a second, so I'm going to skip it for now. You may have heard from cosmologists that we think that more than 70% of the energy content of the universe is in the form of something we call dark energy. So this is a sort of a nickname for something we don't really know what it is. Maybe it's just a cosmological constant that appears in the Einstein equation. You're allowed to add some constant here, lambda times g, but maybe it's something else. And it's 70% of the energy content of the universe. So, you know, we really want to know more about that dark energy. And gravitational wave observations will help us figure out more precisely what the equation of state of that dark energy is. If you're interested in neutron stars, which are, you know, basically stars like some sort of self-gravitating balls of neutrons with typical sizes of the order of 10 kilometers, and more than one solar mass, so like the most dense objects we can imagine. The density in the center of a neutron star is likely a few times larger than the density in an atomic nucleus. We know very little about the physics under such extreme conditions, while gravitational wave observations will help us learn about that because neutron stars are very good sources of gravitational waves. So if you're a nuclear physicist, you should care about gravitational wave observations. Now, if you're an astrophysicist, maybe you want to know how binary black hole system or binary neutron star system form. How many are there? What is the typical mass distribution? What does it tell you about the star progenitors, right? How many massive stars explode and make black holes and live in couples? All those questions we'll be able to assess and address when we'll have many more gravitational wave observations from such binary system of compact objects. If you're interested in gamma ray bursts, well, basically, we don't know where they come from. There's one theory, which is that the short gamma ray bursts come from the merger of binary neutron star systems. So if we see gravitational waves from binary neutron star mergers, and then we see gamma ray bursts associated with them because we can look the direction of the event and correlate, that will be very interesting to learn about the progenitors of those events. If you're interested in cosmology, well, gravitational wave observations will allow you to measure the so-called Hubble constant, that is to say the rate of expansion of the universe, which you may have heard of is actually accelerating. So it's not constant, it slowly increases with time. This Hubble constant, to measure it, you need to know the position and relative velocity of a distant object in the universe. Velocity, we know how to do with the redshift. Distance, it's always very difficult. And gravitational waves here are very important because the amplitude of the gravitational wave is inversely proportional to the distance. So as soon as you measure the gravitational wave amplitude, you have an information about the distance of the event. For instance, the first gravitational wave that was detected last September, we know it comes from the merger of two black holes that happened at something like 400 megaparsec. There's a large error bar because we're just starting, but already it's a very interesting information that would be very hard to measure otherwise. And many other things. I could spend an hour discussing each of those topics. There's a lot of science you can do. And this is why it's really important to have gravitational wave observations. So let me just focus on one.
Very naive question.
Yes?
How do you extremely naive question. How do you define distance in general relativity?
It's not obvious, actually. There are many ways you can define distance. One that is very convenient is what we call the luminosity distance, which is defined operationally by the measure of the flux of light that you get. But you have many other sort of definitions of distance. You can use another one which is called angular diameter distance, which is related to the apparent size of the object. And there should be, you can figure out that there's a link between those two distances. These are very operational definitions of distance. Some are more useful for theorists like co-moving distance or things like that. But what you need to make sure of is that the notion of distance you use is actually related to what you're actually measuring. And in the case of the amplitude of the gravitational wave, what comes in is a so-called luminosity distance. Yes?
Could two gravitational waves interfere together?
Yes, in principle. So these are sort of small, ripples of space-time curvature. If somehow you could make a source of two sources of gravitational waves that were neatly, if you could sort of devise the source in such a way that those waves have the same amplitude and wavelength, and they are in phase opposition, then they could cancel each other. It's just that we don't know how to do that in a lab. That we'll see in the last part of the lecture today that the promising sources of gravitational wave are of cosmic origin, astrophysical sources. And in that case, a gravitational wave emitted by a binary black hole system there a billion years ago will likely not arrive exactly at the same moment as one emitted by some other system that is completely independent. So we're not so afraid of such interferences in practice. Other questions? Nope. Okay, so let me tell you about one, in my opinion, beautiful test that we'll be able to do thanks to gravitational wave observations in the near future when we will have a gravitational wave observatory in space. So I'll talk about detectors next week, and in particular about a European project to have a detector in space called Elisa. So I'm just going to do some short parenthesis and remind you of what is geodesy. Geodesy is this field where the goal is to measure, characterize the shape of the Earth. The way you do that is you nowadays send satellites in space, and you track the motion. You communicate with it through radio links, for instance. And of course, the motion of those satellites is influenced by the gravitational potential in which they are moving. So by tracking accurately the position of the satellite, you have some information about the gravitational potential of the Earth. And so you can measure this way the shape of the Earth, and in particular the so-called geoid. Well, similarly, if you imagine that you have a supermassive black hole, that is to say, a black hole with a mass of the order of 10 to the 6 to 10 to the 9 solar masses, and we know such black hole exists in every center of every massive galaxy like our own. We have a supermassive black hole in our Milky Way galaxy with a mass of roughly 4 million solar masses. Then if you have a small compact object like a stellar mass black hole or neutron star orbiting this supermassive black hole, In some way, it acts a little bit like a satellite, right? Just like the satellites we send around the Earth. And this system is going to emit a lot of gravitational waves. We call them extreme mass ratio in spirals because the mass ratio is extreme and because the small body spirals in the massive black hole. Why does it spiral in? Because as it moves around, it sends out gravitational waves that take energy away with them. And so the orbit shrinks with time up to the point where the small body falls into the big black hole. Elisa, this space-based detector, will receive those waves, will measure those waves, and will then be able to infer the orbit of the small body around the supermassive black hole. And of course, this orbit depends on the gravitational field of the body that is in the middle. So by tracking very accurately that gravitational wave, you'll be able to test the properties of the central object, which we think is a supermassive black hole. So here I'm showing, can I have the mic, please? Thank you. I'm showing an animation, thank you, where you have the orbit, the small body orbiting around the supermassive black hole. The supermassive black hole has this arrow here, which shows you the spin, the direction of rotation of the black hole around itself. As you can see, the orbit is not planar, right? It's actually quite complex. It has a lot of structure. And we're following this motion for 100 or 200 days before the merger. And at this stage, the orbital velocity is already a third of the speed of light. Do you hear the sound? Oh, I don't know. This is supposed to be a transcription in the audio band of a gravitational wave signal that actually happens to be out of the audio band between 10 to the minus 4 and 10 to the minus 1 hertz. So you just shift it so you can hear it, and you can hear some structure. Right now, you could actually hear some beating happening because two of the orbital frequencies were in resonance with each other. So we are 2 months before the merger, and the sound you hear here, right, this is a gravitational wave that Elisa will actually measure. And if you measure this gravitational wave, which has a lot of structure, you can infer what this complex motion was, this complex orbital motion. And from this complex orbital motion, you can infer not only what the mass and spin of the supermassive black hole are, but also what its quadrupole moment and higher order multiples are. So the black hole is not really growing, it's just that the orbit is shrinking and we are zooming in. Okay, so you could hear the frequency that was, thank you, increasing in time. So we'll do some little calculation to explain you why. But basically, the gravitational wave frequency is related to the orbital frequency. If you lose energy, the orbit shrinks. Kepler's third law tells you that the frequency, the orbital frequency should increase, and so the gravitational frequency will also increase. So I like very much this system because I think you can do beautiful physics with it, but also because you can create a new name. So you can make a neologism borrowed from geodesy. So I'd like to call this botriomeladesi from the Greek for black, mela like melanome and melancholy, and botrio for cavity or hole. So this is not official yet, but I hope that in 20 years' time, people will talk about botriomeladesi, which will be a branch of science that allow you to test the so-called no-hair theorem of general relativity. This is a very important theorem. In general relativity, any stationary black hole, any equilibrium black hole, is very simple. It's characterized by only two numbers, its mass and its spin, classical spin, not quantum. So this is quite extraordinary. That is to say, in the universe, black holes are the most perfect, simple macroscopic objects, right? Anything macroscopic, usually you need more than an Avogadro number to characterize them, right? Too many degrees of freedom. A black hole, you give me his mass, his spin, I can tell you everything about it, literally everything. And so in GR, you can show that an equilibrium black hole is indeed characterized only by its mass and spin. And so all of its multiple moments, its quadrupole, for instance, is a simple function of those two numbers. So when we'll detect gravitational waves from EMRIs, extreme mass ratio in spirals, we'll be able to test this theorem. And so we'll be able to test very precisely if the black holes of nature are indeed those predicted by Einstein's general relativity. So that was just an example that I think is very interesting of fundamental physics you can do with gravitational wave observations. Okay, so yes?
Is it known whether our local black hole in our galaxy is rotating or not?
No.
It's measured?
No, it's not measured. So far, we can measure more or less accurately the mass, but for the spin, it's very difficult. We have some constraint on black hole spins from stellar mass black holes, because those live in couple with stars, and there is some accretion disk that forms when the matter from the star is accreted by the stellar mass black hole. And you can study the dynamics of that matter around the black hole. You can figure out that there's an innermost stable circular orbit that is at a certain position from the black hole. And by sort of trying to fit for the observations, and that's very model dependent, you can get a constraint on the spin. Right? So that has been done, and you find spins that can be very large, very close to the maximal spin possible for a black hole. For supermassive black holes, as far as I know, this has never been done. But with the gravitational wave observations we had recently, last September and December, I'll talk about it next week, we are able to put constraint on the mass of the final black hole that was created. And for the two of them, for the two observations, so the first black hole that resulted from the merger of two 30 solar mass black hole roughly made a 65 solar mass black hole with a spin of roughly 60% of the maximal possible spin, and comparable result for the other system. So I took much more time than I thought. So I'm wondering if I should start discussing gravitational wave sources. It's going to be all on the blackboard, so maybe in 10 minutes, it's not really worth it. Probably what I'm going to do is I'll start with gravitational wave sources next week, discuss the sources of gravitational waves, and also the detectors and the observations. And I'll try to be a bit more efficient. And I'm just, in the last 5 or 10 minutes, want to discuss something that is quite important but maybe not so well known, which is that the discovery of gravitational waves, maybe you've read everywhere, like in Le Monde or whatever, gravitational waves have been discovered. This is only partially true. We knew that gravitational wave existed. What has happened is that for the first time, we've seen them directly. For the first time, we have observed the effect of a gravitational wave on a detector that was built on Earth. But if you ask anybody who knew about gravitational waves already in the 1980s, they would have told you, yeah, of course gravitational wave existed. And here is why. We had a couple of systems already that we knew like these. So the idea is that you have essentially two neutron stars. And one of them you are able to see rotate on itself. And this is because neutron stars have a strong magnetic field. There is emission of electromagnetic waves along the magnetic axis, for instance, radio waves. And if the magnetic axis is not aligned with the spin axis, just like the Earth, then you're going to get some radio beam that rotates like that, okay, very regularly, up to several thousand times per second. So, by the way, just try to imagine something that is like 1.4 solar masses, 10-kilometer radius, rotating on itself several hundreds or thousand times per second on itself. That's a neutron star. It's pretty crazy. And if this radio beam is actually aligned with the direction of observation, well, you're going to see this beam every rotation of the pulsar on itself. It's like some sort of cosmic lighthouse, if you want. So these pulsars were first seen in the 60s, but in 75, these two gentlemen, Hertz and Taylor, discovered the first binary pulsar. That is a pulsar that is in orbit with a companion star, which later we figure out is also a neutron star. And you can see a lot of interesting feature in the radio beams in this binary pulsar, because there's a lot of new physical effects that come in. In particular, you're going to have some Doppler modulation of the signal due to the orbital motion. You're going to have some Einstein effect or gravitational redshift effect, because when the radio beam gets close to the gravitational potential of the companion, it's going to get redshifted. And that's going to leave an imprint in the signal you see in your radio waves. Furthermore, you can track the orbit over a very long time, and you can figure out that the orbit has some eccentricity, 0.6 or so, a short orbital period, around 8 hours. So that means that the two stars are basically fitting within the sun. Okay? These two neutron stars have an orbit which is roughly the size of the sun. And you have another physical thing you can observe, and that is the so-called periastron advance. This elliptic motion, it's not a closed ellipse like in Newtonian gravity. There is precession of the periastron, just like the famous perihelion of Mercury, right, which was explained for the first time thanks to Einstein in 1915 by a general relativistic effect. So this is the same phenomenon. Every year, the periastron advances by 4 degrees. So you can measure this combination of gravitational redshift and Einstein effect on one hand, and the periastron advance on the other hand, and that tells you what the two masses of the two objects are. And you find, you know, these numbers here, roughly 1.4 solar mass for each. And by the way, this is, as far as I know, the most precisely measured masses of bodies outside the solar system. It's quite impressive. 4 significant digits. I think people can do even better now. So now what happens? These two compact objects move on this orbit at a significant fraction of the speed of light, maybe 1,000th of the speed of light. So it's not very large, but if you wait for long enough, you know, relativistic effects can become important. And in particular, you have gravitational wave emission. The size of the orbit shrinks by a couple of centimeters every day. Okay? Every day, the two bodies get closer by a couple of centimeters because they are losing energy to those gravitational waves. So that means that the orbital period is increasing also with time, very slowly, by something like 10 to the minus 12 seconds per second. And you can see that also in the radio signal. So you can compare the observation to the prediction from the theory. Since in GR, you know what the rate of change of the orbital period should be for a binary system with given masses that you've already measured, you can make a prediction, which is the curve here. And you can compare that to the observations, which are those points where you cannot even see the error bars because they are too small. And there's a perfect match. This is actually a test of the orbital decay of that system due to gravitational wave emission. And that test is passed at the 0.016% level. So that was already a very important proof of the existence of gravitational radiation, albeit an indirect proof, because this is an indirect effect of the wave emission on the motion of the binary system. And we know most systems like that. And I guess I'll stop there if you have questions for today.
I'm not clear about the frequency shift. Is it the radio pulse emitted by the pulsar, or is it the frequency of the is it the envelope of the radio wave, which is?
So if you look at the signal, you know, it has some sort of envelope like that. And what you do is that you recover that pattern regularly every orbit. If the neutron star was isolated, you would get essentially always the same pattern at exactly the same period, extremely regular. Some of these systems are as regular as the best atomic clock we can make on Earth. But in a binary system, you're going to have some modulation of that, right? It's going to come more or less soon, the next signal, because of that Doppler shift, because of that Einstein delay, and so on. Are there other questions? Yes?
We have an idea if there is a gravitational wave background in the universe and if it carries some valuable information.
A background, for instance, that would have been emitted by some physical process that happened everywhere at a given time?
I imagine that if we put just a satellite in space, we will have a background somehow, and we'll have a certain signal-to-noise ratio. And what is the ultimate limit? And is this background? Oh,
you mean the sources of noise, maybe?
Yes, the sources of
noise. Yeah.
So
I'll talk about that next week. But basically, there are many sources of noise. This is a huge challenge to be able to control of the sources of noise to reach a level of accuracy in your measurement that is roughly comparable to the size of the physical effect you try to see in there. Basically, you have a signal which is almost lost. I mean, if you do nothing, it's really lost in a lot of sources of noise. Then you work a lot for decades, literally. People started building LIGO and Virgo and so on in the 90s, and even before that, they studied very seriously all those sources of noise for decades. So this is a huge amount of work for decades by dozens, if not hundreds of people to understand and control all the sources of noise. And when you do that, then in 2015, you can say, I have an instrument that can measure a relative change in length of the order of 10 to the minus 18. So that's an accuracy comparable to knowing the size of your detector, which is, a kilometer long, or 3 kilometers long, or 4 kilometers long, with an error of the order of 1,000 of the size of an atomic nucleus. Or measuring the distance between the Sun and Alpha Centauri, the closest star, 4 light years away, with an accuracy that amounts to the width of a hair. Right? So to get to that level of accuracy, you have to beat a lot of noise sources. Thermal noise acting on your mirrors, suspension noise, gravity gradient, photon shot noise, and so on.
My question was more, if we put a detector in space,
yes,
then most of the sources of noise are related to the human background somehow,
so,
right?
So indeed, some noise you can beat at low frequency, like the gravity gradient noise at roughly 1 Hertz. And if you want to measure gravitational waves at lower frequency, you need to go in space. And that's the Elisa project I'll mention next week. And then in space, it's not that you don't have any sources of noise anymore. It's that you have different sources of noise. In particular, you still have shot noise. That is to say the fact that when you count your photons at high frequency, you're going to be sensitive to the fact that indeed they arrive at set time and well, how to say this? This is a quantum process, the emission of light, and there is some quantum limit that you cannot beat that sets the noise level at high frequency. At lower frequency, I think it's more related to the differential acceleration noise between the two detectors that make the arm of your interferometer. But again, people have been studying these sources of noise for a long time. And if you want to, well, maybe I can sort of flash this kind of curve, show you the typical gravitational wave amplitude you can measure as a function of frequency. This is the noise curve for the space-based detector Elisa, okay, between 10 to the minus 4 and 10 to the minus 1 Hertz. If your gravitational wave amplitude is above that curve, you're sensitive to it. If it's below, you're not. And same for ground-based detectors such as LIGO and Virgo, which work at higher frequencies. So to get this kind of sensitivities, as I said, it's a lot of work by a lot of people. And you have different noise sources depending on whether you're in space or on the ground. Sure.
Well, thank you very much.
Thank you.